Hi, I'm Adnan Akbar, MPhil in Physics and BS in Mathematics. And today our lecture is about the Coulomb's law problems, part 1. And let's solve them without any delay. We have first problem. Find the ratio of Fe and Fg for two electrons placed apart at some distance from each other. Consider we have two electrons having the masses m1 and m2 and charges q1 and q2 and are separated by a distance r as shown in the figure. Then the forces between them will be Fe is equal to k q1 q2 over r square and Fg is equal to g m1 m2 over r square. As here both are electrons, so they will have same mass and same charge. Then m1 is equal to m2 is equal to m, and q1 is equal to q2 is equal to q. Then relations for the forces will become Fe is equal to kq square over r square, and Fg is equal to gm square over r square. And then the ratio will become kq square over gme square. K is the proportionality constant in case of Coulomb's law. Q is the charge in electron, and G is the gravitational constant in case of gravitational law, and Me is the mass of electron. Then putting the values of these constants, our relation will give the final results to us 10 raised to power 42, which is showing electrostatic force is 10 raised to power 42 times stronger than the gravitational force. We can also solve it for the proton, which will result as 10 raised to 36. Let's move towards our second problem. Where should we place a charge along the line joining two similar charges so that it will be in equilibrium? To solve this question, consider we have two charges. One is a smaller one, Q, and other is a bigger one, 4Q, are separated by a distance L as shown in the figure. To solve this problem, we have two possibilities. Let's move towards first one. Suppose third charge is plus q. If we place on the left side of the charges or the right side of the charges, in both cases it will be repelled and the net force will not be zero. So this possibility will not work, and then let's move towards our second possibility. In case of similar charges, we place a third charge in between them closer to the smaller charge so that net force will be equal to zero and it will be in equilibrium. So this possibility will work, and for the equilibrium, forces acting on the third charge should be equal to each other. Here F1 is the force applied by the smaller charge on the third charge Q, and F2 is the force applied by the bigger charge on the third charge Q. Then relations will be kq dot q over r square, where r is the distance of the third charge from a smaller charge, and L minus r is the distance of bigger charge from the third charge. In this relation, k small q, capital Q on both sides will cancel to each other, and our relation will become 1 over r square is equal to 4 over L minus r whole square. Taking square root, then our relation will become 1 over r is equal to 2 over L minus r, and L minus r will be equal to 2r. Then L will be equal to 3r, and our final relation will become r is equal to L by 3. In case of the similar charges, we always put the third charge in between them somewhere to find the equilibrium point. We have shortcut to solve such type of questions. Here we have a formula to know value of the equilibrium point x in case of similar charges. X is equal to square root of q1 or square root of q1 plus square root of q2 into L, where q1 is smaller charge. To justify just this formula, We have an example where q1 is equal to q and q2 is equal to 4q. After placing these values in the formula, we have the relation x is equal to square root of q over square root of q plus square root of 4q into L. Our relation will become square root of square root of q over square root of q plus 2 square root of q into L. After simplification, it will become square root of q over square root of q into 1 plus 2 into L. Square root of q will cancel to the square root of q, and our final relation will become x is equal to 1 by 3L. Similarly, we have another problem. Place charge on the line joining two opposite charges so that it should be in equilibrium. Consider we have two charges. One is a smaller charge plus q and other is opposite but bigger charge minus 9q are separated by a distance L as shown in the figure. Again, we have two possibilities to solve this problem. Let's move towards first one. Suppose we have two opposite charges of charge on them q and minus 9q separated by a distance L. If we place a third charge in between, then one of these will attract and other will repel, so net force will not be zero. So this possibility will not work. And let's move towards our second possibility. For the equilibrium point, in this case, we place third charge q on the left side of the smaller charge so that attraction of the bigger charge will be balanced by the repulsion of the smaller charge as shown in the figure. And this possibility will work. And for the equilibrium, we know the forces should be equal to each other. F1 is the force applied by the smaller charge on the charge third, and F2 is the force applied by the bigger charge on the third charge. Q over R square, where R is a distance between the smaller charge and third charge, where L plus R is a distance between bigger charge 9q and third charge. In this relation, K, capital Q and Q will be cancelled in both sides, and our relation will become 1 over r square is equal to 9 over L plus r whole square. And taking square root, our relation will become 1 over r is equal to 3 over L plus r. And our relation will become L plus r is equal to 3r. After simplification, our relation will become L is equal to 2r. Then our final relation will become r is equal to L by 2. And to solve such type of problems, we also have a shortcut. Here we have a formula to know the value of equilibrium point in case of opposite charges. X is equal to square root of q1 over square root of q2 minus square root of q1 into L, where q1 is the smaller charge. To justify this formula, we have an example again. Q1 is equal to Q and Q2 is equal to 9Q. After placing these values in our formula, we have relation X is equal to square root of Q over square root of 9Q minus square root of Q into L. After simplification, our relation will become square root of Q over 3 square root of Q minus square root of Q into L. And then our relation will become square root of q or square root of q into 3 minus 1 whole twice into L. Here square root of q will cancel to the square root of q, and our final relation will become x is equal to 1 by 2L. Thank you very much for watching my video. If you have any question, you can ask in the comments section, and please subscribe and like my YouTube channel. Thank you very much.